Okay, so one of the nice things, we are about to finish the content in terms of reactions. We have a couple of cleanup reactions to do, and then we have a section on NMR, of which you'll be starting in the lab. So Terry will start you off with NMR. But the nice thing about that is that we have a bunch of time before the exam to start doing problems in class. So we're going to stop very shortly getting new content and work on problem solving and working with the content we have. So that's kind of nice, actually. The last, we have two things to cover today. So we have this thing called addition to alpha-beta unsaturated carbonyl compounds. And if we take a look, we can add nucleophiles to these things. And we have two electrophilic sites. We're going to see in a moment why. But this carbon is electrophilic, and this carbon is electrophilic. And you'll notice that we're using these things. Here we have a methyl Grignard reagent. And that's, we can think of that as it's an effective source as a carbanion, a carbon with a minus charge on it, which should be a very good nucleophile. It turns out it does. It adds, and it adds at this carbon, and it also adds at this carbon. We get a 72% yield of what we call the 1,2 addition, and that is it adds here, and then we protonate there. And we also get a small amount of addition here. We call this 1,4 addition. And what happens is it adds there, the proton gets protonated, the oxygen gets protonated, and then it reorganizes to the enol. We're going to see the mechanisms for these in a second. We can change our conditions slightly. We're used to Grignard reagents and organolithic reagents, and they're sources of nucleophilic carbon. They're strong nucleophiles, and we get addition here. Now we have another organometallic compound. This is called a Gilman reagent, but it's also a source of, in this case, methyl groups with a negative charge. So nucleophilic methyl. But look at this one. Now we get virtually no addition at the carbonyl carbon, 0%. We get about a 45% yield over here. So what ends up happening is that this does not react with carbonyl carbons. Now we can take our Grignard reagent and change the conditions slightly. A little bit of change of solvent. We do these reactions at higher temperature. This is actually done at low temperature. We add some other metals, manganese chloride and copper chloride, and all of a sudden we get no 1,2 addition. Everything we get is the 1,4 addition. Our methyl group ends up at this carbon. So the reason I show you this is that as chemists, we get the opportunity sometimes to control how the reactions happen. All of these we could naively expect to be very similar because they're a source of CH3-, and we would expect to get similar outcomes. But we get quite different outcomes. So what's going on with the regioselectivity? So if we take a look at our alpha-beta unsaturated carbonyl compound, it's called that because the alpha carbon and the beta carbon are unsaturated. They're a carbon-carbon double bond. This is showing the electrostatic potential map, and we can see that this is the positive part, this is the negative part. So we expect it to be electrophilic down here. And if we use our valence bond description of bonding, we can draw different resonance structures. We've already seen that this contributes a little bit to the carbonyl group, this Witter ionic species. We can then delocalize that positive charge down to the beta carbon. So the carbonyl carbon and the beta carbon are electrophilic. And this helps to explain. So they have partial positive charge. So we expect then nucleophiles to attack one or the other of those. And that's what we see. What we see is hard nucleophiles, strong nucleophiles, typically are going to attack the carbonyl carbon. When we get to less reactive nucleophiles, they actually end up attacking the beta carbon. There is an element of kinetic versus thermodynamic control here. We're not going to get into that. But here's another example. We have a nucleophile. In this case, it's just methylamine. The lone pair of electrons in the nitrogen attack the beta carbon, and we end up with this thing. This is an enolate anion, and it's protonated at the nitrogen. And then we just get a rearrangement. The proton jumps off, jumps on somewhere else, happens to jump on over here. This is just an enol, and then that enol can isomerize or tautomerize into the ketone functionality. So our nucleophile, the methylamine, is attached to the beta carbon, and we end up reforming the carbonyl compound. So that's a fairly common motif. We call that conjugate addition. Okay, so we have two possibilities. We can have 1,2 addition. We call that simple addition, and that's where the nucleophile attacks the carbonyl carbon, and then whatever the proton ends up on the oxygen. Or we can have 1,4 addition, and that is where our proton still ends up on the oxygen, but our nucleophile ends up on the carbon. This is the enol, and it will isomerize to give the ketone. That's the fairly common motif. For the most part, strong nucleophiles favor 1,2 addition, so Grignards and alkylithiums, as well as metal hydride. So if we do a reduction with a metal hydride, we typically will, sometimes we can reduce both unsaturated systems, but with the metal hydride, we can actually just reduce the carbonyl and leave the carbon-carbon double bond intact. So simple addition occurs here at the carbonyl carbon. Conjugate addition occurs at the beta carbon. You'll want to get used to this. Whenever you see an alpha-beta unsaturated compound, the first thing you want to think of is conjugate addition. So you want to look for a nucleophile and look for this addition motif. That's most often what's going to occur. There are other reactions that can occur. We can have Diels-Alder-like reactions, but most of the time, this should be your first thought. So conjugate addition, the mechanism really is just our nucleophile, in this case cyanide, attacks the beta carbon, and we can reorganize our electrons. So we can either put the negative charge up on the oxygen or on the carbon. These are just resonance structures, and this is an enolate. The enolate then gets protonated to form the enol, and that enol will reorganize to give the carbonyl compound. The proton could also jump on at the carbonyl carbon, but if it does happen to end up here, we get isomerization to the keto form. So this reaction goes in high yield. The conjugate addition reaction for cyanide actually goes in 95% yield. We do want to be careful. The fact that we have an enolate as one of our products means that that's a reactive compound too, and the conditions might be such that that could react further. We usually set things up so that doesn't happen, but we quite often get not terribly high yields. This is a good yield, but often our yields are in the 70% range because this can go on and do further chemistry. And we're not going to worry about that too much right now, but we will in a few minutes. So conjugate addition reaction, we can use nucleophiles. One of the nucleophiles we might want to use is an enolate. So you can imagine I've made our traditional, there's our electrophile. This thing is, although it is an electrophile, I'm indicating that it's going to be my intended nucleophile. It's red. So we could pull off that proton, and we can just clip together. We form a new bond. The conjugate addition of a simple enolate to alpha-beta unsaturated ketone or aldehyde will give us a 1,5-dicarbonyl species. Mechanistically, it's as we might expect. We have that acidic proton. We just remove that acidic proton and form our enolate. Okay, this thing is now a nucleophile. So we started off with something I indicated. This is an acid-base reaction. We've now made a nucleophile. We can undergo a reaction with an electrophile. We bring down our electrophile and we just push our arrows. We're forming a bond between this carbon and this carbon. This is the new bond that's formed, and we end up getting another enolate. As you might imagine, one of the things that could happen if you had lots of this substrate around, you could get a polymerization reaction happening. Because this is an enolate, it could be a nucleophile. As it turns out, that nucleophile will be a little bit more reactive, mostly because it's got a small CH2 group there with a negative charge on it. It's a little bit more reactive than this nucleophile. This thing is a more substituted nucleophile, less reactive, more stable. So that's one of the things that helps us to avoid getting, this will react with the starting material, but it'll react at a much slower rate, and this will happen faster. So once we form that enolate, The last reaction is just acid-base reaction. We just remove a proton. We can protonate directly on the carbon to get our 1,5-dicarbonyl species. We could also protonate here, in which case it's going to end up just isomerizing to give us the 1,5-dicarbonyl anyhow. So this is the mechanism. Now, one of the things I'm going to start really emphasizing to you guys, because now you're ready to accept it, most of our reactions we can break down into acid-base reactions or nucleophile, electrophile reactions. I'm not talking about redox or radical reactions here, but most of the chemistry we have seen can be broken down. And here, this is the mechanism. Step 1 is just an acid-base reaction. We're just removing a proton. Step 2, once we've removed that proton, we've made a good nucleophile, and we have a good electrophile up there. So the second reaction is just a nucleophile-electrophile reaction. And the last step is just an acid-base reaction. You will see this over and over and over again, and that's what you want to get used to, is that you just have a bunch of acid-base and nucleophile-electrophile reactions. That's what almost everything we've done in this course is. Just wanted to show you at the end this base. So notice the base, we use the base up here, we form water, and then the water comes back down, proton gets removed, and the base reforms. So the base is needed in a catalytic amount. That's often a question I will ask. I will ask you to do a reaction, and then I may ask if the acid or base needs to be in a full equivalent amount or a catalytic amount. What you will find is very often the acid is catalytic. The base can be catalytic, or we may also call it base promoted, in which case we use up all the base and we need a full equivalent. The reaction is wide in scope. It's known as the Michael addition, after some chemist named Michael, and that was his last name, not his first, but that's what it's named after. It works with a variety of substrates. Not only can we use that normal alpha-beta unsaturated ketone, our unsaturated carbon-carbon can be a triple bond. As long as we have at least one pi bond there, that can be the unsaturated portion. And our electron withdrawing group need not be a carbonyl. Maybe it's something like a nitrile or a nitro group. All we need is a carbon-carbon double bond with a very good electron withdrawing group attached to it, and this becomes an electrophilic carbon. So here we see two reactions. This is familiar, acetoacetate. This is ethyl acetoacetate. We know that we can pull that proton off. That forms our enolate. Our enolate will attack that carbon, and we end up forming this thing eventually. So go through the mechanism. You'll notice you can see this part right there, and all you've done is add, that's your new bond that you've formed. You formed between here and here. In this one, now we're using diethylmalonate. Notice diethylmalonate functionality is still in there. There's our our acrylonitrile. Okay, there's our new carbon-carbon bond. We've just attached, we've removed that proton, make it a nucleophile, and that reacts with the electrophile. So our acid-base reactions are to either produce a good nucleophile or a good electrophile. Quite often that's the first step. We protonate carbonyl groups, it makes a very good electrophile. We deprotonate a ketone, that makes a very good nucleophile. Okay, so the acid-base reactions typically provide us with either a very good nucleophile or a very good electrophile. Then we have our nucleophile-electrophile reactions, and often there's another acid-base reaction to wrap things up. So we get higher yields with more stable enolates. Strong enolates do get someone to addition as a side product. We can also use an enamine. An enamine is very much like an enolate, but instead of a negatively charged oxygen, we have a neutral charged nitrogen functionality up here. They're not as good a nucleophiles as enolates. They're slightly less nucleophilic, so we have to heat these reactions up. But that actually works well in this reaction because we get almost exclusively 1,4 addition in the case of enamines. And we get this aminiamine intermediate, which we can work up with water. Remember, now we have a positively charged nitrogen. We can draw a resonance structure. This is a very good electrophilic carbon now, and it'll react with a very weak nucleophile like water, and we end up series of reactions getting rid of the amine inserting an oxygen there. We've been through that mechanism. So I told you this is an enol equivalent. Down here, question, can you draw the enol equivalent? You may want to give that a try. So here's a nice reaction, the Robinson annulation. And this one, when you first look at it, it's kind of daunting because you just see this, and all of a sudden you get a whole bunch of things going on. What is happening here? So let's think about our conditions. We have a couple of compounds. Which one of these is an electrophile? Well, they're both electrophiles. Which one is the better electrophile? How many people think this is the better electrophile? There's something called MAGID's, M-A-G-I-D, rule, and it says when you have an alpha-beta unsaturated ketone, try doing the Michael reaction first. Try doing the conjugate addition reaction first. So what that's telling you is this is actually a good electrophile. This is probably the best electrophile. So this is an electrophile. Can we turn it into a nucleophile? We have base. Yes, we can. We can turn it into a nucleophile either by letting it isomerize to the enol, which are okay as nucleophiles, or by removing a proton using a base to make a very good nucleophile. So after we analyze, the first thing we may want to do then, actually I'm going to write a little smaller so I can maybe... When I say a ketone, when I was a student, I would often put my hydrogens in there, and I would put them both there, and then I'd start working there just so I don't forget, right? So that I know those hydrogens are there. And I have some base. I don't care what the base is, some base. Could be hydroxide, could be anything. I'm just going to call it base, and I'm going to put a lone pair of electrons there. The first step in our reaction then simply removes a pair of electrons. I'm sorry, a proton. And we get our negatively charged carbon. This is a good nucleophile. Now we're going to throw our electrophile in, and I'm going to throw it in like this. Our electrophile was always there, but now I need to use it, so I'm putting it there. Putting it very close to where I think I'm going to have a reaction occur. And I'm just going to attack that carbon, and this is my new bond. So now I have to form 1, 2, 3 carbons. I'm going to go 1, 2, 3 carbons, and 1, 2, 3 carbons. I have a double bond here. That's what my arrow pushing has indicated. Everybody should be able to do that. So if this is carbon 1, this is 2, 3, 4. This is carbon 1, 2, 3, 4. It's another little thing that you can do to try and keep track of things. Take as number the carbons, and now I'm forming a bond between carbon 1 and 2. There's carbon 1 and 2. I'm moving a carbon double bond from between 2 and 3 to between 2 and 4. So I need to have I'm between 3 and 4. There's my double bond and my oxygen. Okay, so these little things can help you keep track of things. Now what's this thing going to do? Oh, a couple of things. We can draw a resonance structure for this. That's just a resonance structure. We just want to remember it. Same with this. I can draw a resonance structure for this where I have the negative charge on carbon 3. But we also formed our protonated base. Our protonated base can now act as a proton shuttle. It can deposit that proton somewhere else where we might need it, okay? And I think I'm going to put it here. I could put it there, I could put it here, but if I put it here, now I don't want you to get stuck up on these things. In our systems, typically there's lots of things that can act as proton shuttles. We typically will use our protonated base just for bookkeeping purposes to see whether or not we use up our base or not. But there's lots of things that can provide that proton. That thing can drift around and pull a proton off one of the starting ketones as well, right? So there's lots of things that can provide that proton. And the other thing you should write down on the beginning of every midterm, protons jump off, protons jump on. When we need a proton, look and see if we can get a proton. Are we under acidic conditions? There's lots of protons. Are we under basic conditions? Then we got to think about what's going on, okay? So we can just reform our carbon-oxygen double bond, pull off this proton, reform our base. I'm going to put my other proton there, and we had this proton here. We had those protons. Okay, what is this thing? This is a 1,5-dicarbonyl. For bookkeeping purposes, is there anything I forgot? What's the other product of this particular reaction? I pulled a proton off something. What did I pull it off of? Right, so I now have my bases around here too. So this is just the first step of the reaction, is the formation of that 1,5-dicarbonyl compound. Now I still have base around. I can pull off protons. I can do things with base. What did we say about a little while back? We talked about the aldol reaction. And intramolecularly, we said that 1,4, 1,5, 1,6, and 1,7 dicarbonyl compounds will undergo a self-reaction, a cyclization reaction. We have a 1,5-dicarbonyl compound. So let's just draw it. We're going to now pretend that we're starting a new reaction. Our reagent is this thing. And I'm going to do this. 1, 2, 3, 4. Oh, sorry, I should have done it this way. 1, 2, 3, 4, 5. There. I have a 1,5-dicarbonyl compound. Here's an easy way for me to draw it. I wanted a 1,5-dicarbonyl. I made this compound 1, and then I numbered out, and I know I have a carbonyl at the 5 position. So that's the same thing as that. I'm now going to erase my numbers. That helped me get there, but they're kind of in the way now. I have base. It's looking for a proton. Where can it get a proton at this point? There's 3 places it can get a proton, right? It can get a proton from here. Well, actually, there's more than 3. It can get a proton from here. It can get a proton from here. It can get a proton from here. And it can get a proton from here. It can also, the OH can also add to the carbonyl, add to that carbonyl. All of those things are happening. So we have to ask ourselves, what's the most likely things that are going to happen? We can add to the carbonyl compound, not going to lead anywhere, just going to come back. I can pull off a proton. I already had this proton off and I didn't do anything with it. Why not? Why did I not do an intramolecular cyclization there to form a 4-membered ring? Well, 4-membered rings we can form, but they're hard. If we can form a 6-membered ring instead, that should be a lot easier. What if we pull off this proton? If we pull off this proton, there's 3 of them, but I'm just going to draw one. I'm going to go all the way to here just because it's easier. And I'm going to draw my carbonyl kind of weird. 1, 2, 3, 4, 5, 6. Okay. Now I've achieved a conformation. I can just form a carbon oxygen or carbon double bond, carbon bond very easily. So I now get this. and I have O minus, and I have, this is the new bond that I formed, okay? And I have a carbonyl there. Oh, what else did I do when I removed that base? Now I'm just looking for a base, a protonated base. I'm just looking for a proton, and this can remove a proton from our base, our protonated base. Okay, boom, I've made my cyclic compound, right? That looks very familiar to that thing down on the right. That's an intramolecular aldol addition, and now the last step of the reaction, we just have to remove a proton from this position and then eliminate that oxygen, and we end up with our alpha-beta unsaturated ring-closed product. This one? Well, there's 1, 2, 3, 4, 5 are beta dicarbonyl compound. And then there's the methyl group right here, right? To the right of that. Yeah. That's actually a requirement for this reaction. If you had an aldehyde there, then you cannot do this reaction because you need this carbon over here. Okay? So let's take a look at what we've done. This is a little bit simplified version. So, and what I've done here, although I can't see it very well, here's our potential, our intended nucleophile. We're going to remove that proton, and we're just going to, actually we're going to remove that proton, and we're going to form a bond between our alpha proton, our alpha carbon, and one of the electrophilic carbons on this molecule. We're going to always remember that we're going to try Michael addition first, conjugate addition first. We're going to form a bond between there and there, and we end up with this product. We did that up there. Then we just kind of redraw it, and we have 1, 2, 3, 4, 5, a 1,5 dicarbonyl compound. Enolate addition to alpha-beta unsaturated ketone always gives you a 1,5 dicarbonyl product. And if we have a methyl group over here, we now have opportunity to form a 6-membered ring. So we can now remove a proton from there and clip on. That's our nucleophilic carbon. That's our electrophilic carbon. Notice now this functionality was the intended nucleophile. Now it becomes the intended electrophile in the second step. So we've switched. Okay? This is the best electrophile here. Now, why is this the best? Why is this a better electrophile than this? Why would, once we remove this proton and form the negative, why won't it react with this? Why does it react with this instead? Okay, so why? Think about it for a second. Over here, right here, why does this not just react with another molecule that's way over there? Okay. How many people think they know why? Okay. No? Okay. But think about it for a second. I have a molecule here and a molecule here. Okay. I can react with that molecule, but I have a molecule I can react right here. I'm attached to it. Can't get away. What's it going to react with? It's attached. It's a proximity effect, right? Intramolecular reactions happen very fast because the electrophile can't get away. It's right there. It's going to keep bumping into it until it forms a bond. Intramolecular reactions, you should write this down, occur very fast because the nucleophile and the electrophile are attached to each other. They can't get away. So, yes, carbonyl groups are not as good as they get more and more sterically congested. This is a very good electrophile, but this would be a bimolecular reaction. This is an intramolecular reaction. Intramolecular reactions occur faster if they can achieve a good conformation. So, to form the four-membered ring, it can't get close enough. Okay, so here we could react this carbon with this carbon, can't get away, but it can't get close enough because it can't achieve a good conformation. So 5 and 6-membered rings form readily. You should write that down next to your intramolecular reactions happen fast. 5 and 6-membered rings, easy to form. 3, 4-membered rings, harder to form. 7-membered rings, also hard to form. Not as hard as 3 and 4, but still hard. Okay? Then, once we do that ring closure, all we have to do then is the condensation reaction. We just have to have base to remove this proton and this OH group to form our dehydration product. I found, you'll notice I go to this website a lot. Anybody looking, it's called Mastering Organic Chemistry. You can actually pay for this site, but he also gives a lot of free stuff. I haven't paid for it. I find a lot of stuff on there for free. But he has a lot of helpful things with some descriptions, and I put the links below here to these sites. But this one is nice. He breaks it down mechanistically. This is a very similar reaction, but instead this is our ketone, and we're going to add it to this. We didn't start with a cyclic compound. But the first step of the reaction, just a deprotonation, an acid-base reaction. The second step, 1,4 addition, electrophile reacting with a nucleophile. Nucleophile attacking electrophile. Last step of the reaction, acid-base reaction. That is what we did up there. Acid-base, nucleophile, electrophile, acid-base. Then we go to the next step of the reaction. Kind of similar things. Once we got our 1,5, we did an acid-base reaction. We did an intramolecular nucleophile-electrophile reaction. We did another acid-base reaction. We protonated it. Then we decided we wanted to deprotonate it, but we took a different proton off. So we had 2 acid-base reactions. And then finally, this reaction, it's an elimination reaction. But if you think about the reverse reaction where a nucleophile would attack the electrophile, this is also, in essence, a nucleophile-electrophile reaction. But in this case, we're eliminating a nucleophile, right? It's just the reverse of the nucleophilic addition to a carbon-carbon double bond, this reaction. Okay? So just acid-base and nucleophile-electrophile reactions. That's everything that's there. So all you have to do, that's why it's so important to be able to look at a molecule and ask myself, what's the most acidic hydrogen? Okay? That's the one most likely to be removed. Once you remove it, ask yourself, I've now formed some sort of anion. Can that do something? If it can't, put the proton back off and take the next acidic proton off. Maybe you will then form an anion that can do something. And that's what happens here. We have a choice. Where were we? We can pull off this proton or this proton. We can also pull off this proton, and we can pull off this proton. That would also lead to a 1, 2, 3, 4, 5, 6-membered ring. It would give us a slightly different product. As it turns out, that is one of the side products that occurs from removing one of these protons and making that. It gives us a slightly different product that has some strain on it. It's not as easy to form. You might try it, but that would be one of our competing reactions. When we draw these reactions too, don't forget other reactions happen. That's what gives us side products, those other reactions. This reaction is going to go largely in this direction. Okay? So this wasn't magic after all. Bill Nye would say it's science. But here we see now, we set our 2 up, our different colors. This is our final product. This is nice. Now we can look, we can see where all the carbons are from the reactants, right? And we formed a 6-membered ring. Organic chemists love forming 6-membered rings because they can make useful things with it, things that have biological properties. medicinal things. So we've made 2 new carbon-carbon bonds. We made a carbon-carbon single bond and a carbon-carbon double bond, and we made a new 6-membered ring, and that 6-membered ring has lots of functionality in case we want to do more stuff to it and make bigger molecules. Okay, so now we have one last reaction, and I'm going to ask you guys to help me out here. So let's take a look, let's analyze this reaction, and let's figure out what can happen, okay? There's a missing component here, which I'll tell you at the end what it is, and it's actually, it's just an H+, but I don't want to confuse you. We have 3 molecules. We're not used to seeing 3 molecules. We're used to seeing 2 molecules, but now we have 3. So what are we going to do? Well, we're going to look and see, what's going on? There's acid here. Normally, the first step of any reaction, you protonate something, and you could do that here. You could protonate something, but you don't need to. Let's take a look then. What is the best nucleophile up there? How many people think it's this thing? Okay, I'd like to see a lot of hands. I put the lone pair of electrons there to help you out here, okay? That is the best nucleophile. Okay, so we have our nucleophile. Is this a nucleophile? No. This a nucleophile? It can be. We can make it a nucleophile. We'd have to do stuff to it. We'd have to either make the enol or remove the one of these alpha hydrogens. It can be a nucleophile. But for now, let's say this is this an electrophile? Yeah, this is an electrophile. This electrophile. Which one of these is a better electrophile? The one with the tiny weeny hydrogens on it, or the one with the great big methyl groups on it? Okay. So this is our best electrophile. So the first step in our reaction, let's take our best nucleophile and react it with our best electrophile. And when we've determined that, we can start analyzing these 3. Which is the best nucleophile and which is the best electrophile? What would happen first? Our nucleophile is going to react with our electrophile. So there we've identified it. We have our first step in our reaction, then we're going to react our nucleophile with our electrophile, and what's going to happen? We're going to form this compound, which is an even better electrophile. We used up our nucleophile. We used up our electrophile. We've made a new superelectrophile. Okay? New superelectrophile. Now, the missing component here is an acid. This is an acid-catalyzed reaction. It can also be base-catalyzed, but it gets messy. Acid catalysis works well. The whole purpose of the acid, actually, is this is the next thing. That's the nucleophile we can make from that thing that's still dark-colored, okay? We can make this enol. I do see it there. I can hardly see it. There it is here. That's indicating it's a weak electrophile. We can isomerize it to the enol, and that's a good nucleophile. Now we have a nucleophile, a superelectrophile. They're just going to react, okay? So we're going to form a carbon bond between this carbon and this carbon, and it's going to give us some product. So let's take a look at the reaction. This is the overall reaction. We've clipped together. We made our super electrophile, and then we made a carbon-carbon bond to there. Here we see there's the acetone. This came from the formaldehyde, and this came from the dimethylamine. This is called the Manich reaction. It's very useful. It's used all the time. It's wide in scope. We have to have formaldehyde. Okay? Now, the reason we have to have formaldehyde occurs right here. If we have a carbon with alpha protons on it, we won't stay that iminium cation. We end up forming an enamine. But because it doesn't have any alpha hydrogens, it stays at the iminium, and that's our superelectrophile. Okay? And that thing then reacts with the enol, and we end up with our Manich base. Okay, that's pretty good timing. That's the last reaction for now. I have a few cleanup reactions we want to talk about. We're going to talk about NMR. I have about 3, maybe 4 content lectures left, few reactions, very few, and NMR. And then the rest of the period we're going to spend doing problems. So I'll think about how I want to do it. It's too bad the class is so large. What I would like to do is break it into groups and then do problem-solving session as groups in class, but there's too many of you. But what I really, really want from here on forward is interactive. So I want you coming to class ready to do some things. Raise your hand when I ask questions, and because I really, really want you thinking about these things. Here's our summary of the reactions from this chapter. We did aldol reactions, then we did crossed aldols, intramolecular aldols, the Clason, which is a lot like the aldol, and we had all those. Today we did conjugate addition, Robinson annulation, and the Mannich reaction. Notice these last two chapters, we formed a lot of carbon-carbon bonds, and we made a lot of 5- and 6-membered rings. So synthetically, these reactions are actually very powerful, and it even gets more fun because there's a lot of opportunity for imparting stereochemistry in a lot of these products. And we're not getting into that. That's for advanced organic. But you can actually do things to make preferred stereochemistry in these